Hello, everyone. My name is Shayan. I'm going to be talking about high availability in MySQL with a clustering solution called Group Replication today. I'm a software engineer a little bit about me, I'm a software engineer at Canonical. I work on the data platform team, which is like a relatively new team. And so to go over today's agenda, I'll be briefly talking about why we need high availability with databases. I'll go over some distributed database concepts. These are like necessary to understand what group replication is doing and why some of the design decisions were made for group replication. Then I'll talk about self-healing, basically how group replication or any database system self-heals from certain failure scenarios. And then I'll be doing a demo of some of the work that we've been doing, and especially with something called operators and a technology called Juju. So, high availability, why is it needed? So let's assume you have a node somewhere where you're running your database, whether it's MySQL or any other database. You make your client, you're making a query, you get your response. But however, if something goes wrong with that node, whether it's like a hardware failure, network failure, something with the program, the issue is that your client will face a downtime. Like you won't be able to get responses. It will be visible that your system's down. So to combat against this, you would add replicas to your database. So this is basically a clustering solution. This is a general problem, why you would need clusters. So that if one of your node goes down, you have standover, failover, standby nodes that you can direct your traffic to, whether it's read or write, and your cluster is still available as far as the client's concerned. So what are some requirements to adding nodes to your cluster? Some of these are like automatic failure detection is like a must-have. You don't want to be detecting that like one of the nodes is down and figuring out how to recover your cluster from that, because usually if the primary goes down, the primary which is getting all the writes, you don't want to be able to you don't want to have to manually go in and change your primary. So you want some sort of failure detection so that the system itself can detect the failure and fail over to a new node that's up. You want primary election, that's like following the previous point. You want to be able to automatically elect a new primary so that your writes are seamless. But because of that, you need transparent routing. The reason for that is your client is usually going to be hitting an endpoint where they'll be directing their write traffic to an endpoint, which gets translated to whatever the primary node is. So that if you have transparent routing, then you don't need to change anything. You're still hitting that endpoint. That endpoint just points to the new node that's the primary. Some nice to haves include load balancing. So since you're adding redundancy by adding new nodes, it's nice to direct your read traffic across or distribute your read traffic across all the nodes. That helps you with distributing read traffic, but also MySQL Group Replication also has multi-primary, so you can split your write traffic across multiple nodes, which is pretty cool. Self-healing, so again, that sort of covers any failure scenario, and having the cluster recover itself is a really nice thing to have. And another thing is observability. You would ideally with any software system you would want to have a way to look into what's running in your cluster, in your system, and get notifications if things go down. For example, a node goes down and you would want to get a notification so that you can go and provision a new node so that you are, maintaining a minimum level of availability in your cluster, especially if you have read traffic being distributed across the cluster. A node going down means reduction in efficiency or read performance, so that you get notifications, you can add a new node, and then your traffic goes back to normal. So adding redundancy usually increases complexity. The reason is, before you were dealing with one node, and that's the only node you have to worry about, so you're working on a single process, a single node. Adding more nodes means you're introducing a new tier of problems you have to think about. One of them is quorum. So what is quorum? Quorum is basically, imagine you have a cluster of 5 nodes. You have a client reach out to one of the nodes, which is the primary, and it's directing some write traffic to it. You want to make sure that this data that is being written to this node is being persisted across your cluster, because it's not just one instance, it's multiple instances of the database running. So what happens if you only persist it to one node, the primary, and the primary crashes before it can replicate that data to the other nodes? You basically have loss of data. So what you can do is you can have a write quorum, which basically defines the minimum number of instances to replicate your data to before you tell the client, okay, I've persisted your data. And usually the rule of thumb is that you want to have your write quorum be more than half the number of nodes in your cluster. The reason for this is it's to ensure that there are no two concurrent writes. If you have multiple primaries, there's only, if they're conflicting transactions, for example, like a bank is a good example is like a bank account. You're incrementing your bank account balance, and some other node in a multi-primary situation, like someone else is also incrementing the same bank account. You don't want to have things operations interleaved. You want to make sure that if there's a conflicting transaction, you want to only accept one of those. And when you have write quorum more than half the number of nodes, you're ensuring that there's at least one node at which there'll be a conflict. Because, for example, you have a cluster of 5 nodes here. If you're updating the bank account balance of a user, you're making sure that 3 of the nodes get the data persisted, and then a conflicting transaction comes in to another node, like the leftmost node that's not part of the majority. And when it tries to write the data to at least 2 other nodes, there's at least one node that has a conflict, and you're able to detect this conflict. So this also helps you maintain redundancy. So in the case that a couple of your nodes go down, you still have your cluster and you still have you're protected from loss of data. You would need to crash more than half the number of nodes in your cluster to have availability issues, but at that point, there's something called majority. So because you're waiting for a majority of the nodes to acknowledge a transaction, if more than half the nodes of your cluster go down, your cluster is not going to be able to write anything because it's loss of majority. So in this case, if 3 of your nodes go down, you need at least 3 nodes to make sure a write is persisted, and you don't have that. So no writes will come in, no writes will be persisted in the system. The other thing is you want to make sure that the read quorum, which is similar to your write quorum, your read quorum is how many nodes you want to confirm your data. If you're reading a certain row, you want to confirm that that row doesn't have conflicting information. You want to confirm it on a majority of the nodes, or in this case, that's what the read quorum refers to, the number of nodes that you read from before you tell the client, okay, this is the data, the latest data that I have for that row. You want to make sure your read quorum and your write quorum are more than the number of nodes, and this ensures that there's no concurrent read and write. If you're trying to read stale data, there's going to be at least one node where you will have a conflict and you'll have the latest data. So if your read quorum is 1, then you need to make sure your write, if you want immediate reads, it depends on your workload. So So if your workload is geared towards efficient reads, then you want to make sure that your read quorum is 1, then your write needs to be persisted on every node before you tell the user your write is persisted, or the client that the write is persisted. Then you can easily read from any node and you have the latest data. If your write traffic is very heavy, then you may persist it to just 3 nodes, but that means your reads are slower because every time you read something, you have to go to at least 3 nodes before you can tell the user what the latest data is. I hope that sort of made sense. Another major concept is the cap theorem. The cap theorem is like something that's been like around for like decades. I think it was like sort of something that like was discovered or like thought of in the 90s. It basically applies to any distributed system. It means the cap theorem, the cap is like CAP stands for consistency, which means that all of the clients view the same data. That means that if I write some data to a database, if I query the data, I expect to get the data that I wrote. I don't expect to get stale data that was like effective before my write. Availability means that all the clients can find a replica of the data in the case of partial failures. That kind of goes back to like the failure scenario I presented earlier. It means that your cluster is available as a unit. That even if there's like some nodes that crash, the client can still write and read from your cluster. And partitioning refers to partitions or partial failures of network failure. That means that like if there's like, imagine your network gets partitioned in a way that like you have 5 nodes and 3 nodes can connect to each other and the other 2 nodes can connect to each other. You want to be able to still function as a cluster in that scenario. And the cap theorem is basically that you can only choose 2 of the 3. And if you think about it, if you're thinking about consistency, then and you're thinking about partition tolerance, so you want your cluster to be up and running, and you want consistency that like your writes are persisted, then your availability might suffer because partition tolerance means that like some nodes crash. That means that by definition, some of your nodes are not going to be available. That means that you can't, if you tolerate failures in your cluster, then you might have to compromise on availability. If you think about availability and partition tolerance, then you kind of give up on the fact that like your writes can be persisted to every node. So by default, you can't persist your writes to every node because you have a partition tolerance, because you have a network partition. You can write to every node. You can propagate those writes to every nodes, every one of the nodes in the cluster. So this is kind of like very widely accepted, and all the databases that you have are making some sort of decision on like the cap theorem. Usually relational databases are strongly consistent. That's like, so I usually don't think about it as like a Venn diagram, even though it's like positioned as a Venn diagram here. I usually think about it as a triangle where you're trying to place a point on the triangle. You can't have all 3, but you can have like, you can let go of some of the partition tolerance so that you have more of it, like it's like there's trade-offs. You can have, if you want strong consistency, which means that like every node in your cluster has all the writes, then that's a strong requirement, and that means you have to choose either partition tolerance and availability from one of those 2. If you have eventual consistency, which is what MongoDB does in some cases, even MySQL Group Replication, as I'll get into it, if you have eventual consistency, which means that you may have stale data, but eventually your writes will get propagated to the node where the stale data is, then you can have both partition tolerance and availability with some like compromises with the 2. I just wanted to post the slide so that like I can like sort of showcase that every database sort of makes a decision on the CAP theorem. And MySQL usually goes for availability and consistency. If there's a partition tolerance in MySQL or MySQL clustering solutions, then the cluster is usually not available. Like if we go into that scenario where like you have 5 nodes and 3 nodes can communicate with each other and 2 nodes in a separate network are communicating with each other, then you'll have an issue with the cluster, because the 2 nodes that are isolated will not be able to do any writes, if that makes any sense. One last thing I wanted to discuss was two-phase commits. So this is like a concept with distributed systems, not only databases. It's a solution to like, how do I commit to this cluster given that there are individual entities that make up the cluster, like 5 nodes. If I have one primary, how am I going to persist this across the cluster and confidently say it's on most of the nodes? And the solution to this is like two-phase commit, which basically the primary, being the coordinator, will ask everyone to all the participants, which include itself and all the other nodes, to vote on whether something can be persisted to the database. If any one of them says no, or a majority of them say no, then that transaction is rejected. If majority of them can say, I can commit this, then the coordinator will tell the participants, okay, I've made my decision, we're going to commit this or we're going to abort this, and the participants do whatever is sort of the decision that's made. This is sort of like a solution for consensus. It's like consensus-based decision making. It's not completely foolproof because between like voting and like actually making the decision and like executing on the decision, something can go wrong. A cluster can go into like a network partition, and then you have issues because you thought you made a decision, but that decision is not persisted. So it's not foolproof, but it's better than like the alternative, which is not using this mechanism. So that was a little too detailed, and these are topics that like if you were to take a systems course, you would spend like multiple lectures going into sort of the details around this. I just wanted to present these so that I can talk about group replication. So why MySQL? It's one of the most popular databases. This is like a developer survey, but like it kind of reflects how popular databases are, what popular databases there are. Oracle here is like very low, but like in reality, it's kind of as popular as MySQL. But it's like one of the most popular databases. And so obviously, if a lot of people are using this, a lot of corporations are using this database solution, then you want to make it foolproof and offer a lot of the nice to haves and the requirements of like clustering that I went over earlier. So let's go over some like terminology for MySQL. Async replication is referred to as asynchronous replication. It means that you have secondaries. The primary gets a write, it will replicate that to the secondary, but asynchronously. It won't wait until the secondaries have all the data before returning a response to the client. That means that if it's possible that a secondary, like a primary does not need to wait on a secondary to get the data. So it's possible that the secondary has stale data or like old data, so to say, and it's possible that this is not a foolproof clustering solution, right? It's possible that the secondary goes down and the primary doesn't know about that. It doesn't really care. It just gets the data from the client and then it tells the client, I've persisted it. And then once it has persisted it, it asynchronously replicates it to all the secondaries. In the case of async replication, imagine the source is the primary. This is demonstrating what happens in the case of async replication. So the incoming error is like the client telling it to execute some transaction, it persists the transaction to its bin log, which is called binary logs. In databases, there's usually something called write-ahead logs, which means that before persisting something to the database, it will write to a log for every transaction. In the case that like a cluster goes down and then it restarts, it goes to the write-ahead log and then like tries to reconcile what data it has with the write-ahead log, and that's like a safety mechanism. So bin logs are just, imagine they're like a log of transactions. Before it relays all these logs, relay logs are just like a copy of the bin log on a replica, but they're not its binary logs. It has its own bin log because it's possible that it got the primary streamed some amount of data to it that it hasn't applied to its bin log yet, but it needs to keep track of this data. So the idea is that like we're not going to wait on any of the replicas to like apply the transaction to their bin log before I return to the client. In group replication, I'll come back to that slide, it's different. Once I get once I get a command to commit some transaction, I'm going to make sure there's consensus across the cluster, and that most, if not all, of the members can commit that transaction to their databases before I write it to my database and return to the client. So that's why I sort of went over some of the consensus concepts earlier. So with group replication is like not just one solution. It's a highly available solution, and it contains multiple components to make it work seamlessly. It's different than async replication because any transaction that comes to the cluster is persisted across the cluster, so it has a write quorum of more than half of the cluster because of the consensus. It makes sure that the write can persist to all the databases. So that's the clustering solution, right? Like the cluster itself, it has automatic detection of like failures. Like if a primary or any of the nodes go down, there's automatic detection of this and an election of a new primary, or like a removal of that node from the cluster, so that when writes come and the consensus is being decided upon, that node that's unavailable or non-responsive is not considered as part of the cluster. But that's not enough. Like we need a router, a way to, the router is a piece of software that's very lightweight. It's intended to be run with your client application, and it's something that will know what the primary of the cluster is and what the replicas of the cluster are. And that way it will be able to route your read traffic and write traffic transparently. So if the primary changes, whether because of failure or just routine change, the router is subscribed to the cluster, it gets a notification, and the client will use the same protocol that it would use to communicate with the database. It'll use the same protocol with the router, and the router will seamlessly just turn around and proxy the traffic to the cluster. It's also like a load balancing component because it can transparently like route your traffic to all of the cluster with read-only endpoints. And then there's like a component called MySQL shell. It's an administrator tool which will allow you to make adjustments to your cluster, or if you have like failover scenarios, then it will allow you to recover from those scenarios. So we went over this slide. I'm going to skip over it. So what does group replication give you? It's kind of dynamic. It allows servers to join or leave at any time. So it's a group of nodes that are like inherently connected through some protocol. It allows for failure detection. So like there's something called gossip protocol, which basically means that all the nodes it'll try to gossip with the other nodes on a different port, on a different sort of, on a periodic basis to make sure that all the nodes are responsive. And if that's how it detects like a node being down or like a network partition. And if it detects any failures, if it can recover from it, it will automatically recover from it. So like if your primary goes down, it will automatically elect a new primary, and your router will get subscribed to that primary change, and your application will seamlessly just continue writing to the new primary. It doesn't need to know anything. There's observability. It allows, MySQL shell has all these utility tools to allow you to observe what's going on in the cluster. And security, I realize this is a security conference, mainly geared towards security, but like, the gossip protocol I mentioned, or like the internal protocol it uses, it can be encrypted with TLS. So everything is secure from end to end. Even in transit, all your traffic is secured from the client all the way to the router, from the router to the server. So this is like an example of like a cluster set. So like, let me take a second here. So like this is a group replication cluster. We went over this just a second ago. We have a cluster here, and then we have router. You can have multiple routers, so they're kind of embedded with the application. So like if I'm running a reporting application and an application that generates data like a web server, they have their own versions of routers. These routers will route traffic read write or read only based on they have different ports, and they will route them to the primary or the replicas. But it's possible to set up an async replication between multiple clusters with group replication. And the reason you do this is so that if something goes wrong with my cluster here and I need the data available, you basically have an async replication to another group. And if something goes wrong with Rome, a whole availability zone, then you can seamlessly just tell all the routers that the primary cluster, not a primary node, the primary cluster is now in Brussels or Lisbon. And this is good because this is like redundancy of the cluster itself. But it's also good because you can route all your read traffic seamlessly. The router accepts all of this, and the router is sort of very lightweight, and it's programmed to seamlessly route primary write traffic to the primary cluster. So this is like one layer more complex than group replication. Another layer, they've recently added read replicas, which is like async replication. Like imagine, so like group replication, there's a limit on the number of nodes that can be in your group. That's 9 instances. If you need more than 9, like for example, you have millions of reads per second, 9 nodes is not going to cut it. What you can do is you can add read replicas that set up asynchronous replication between the cluster and the node. So the group, again, will not include these read replicas in its quorum. It'll just like shovel all the data it gets asynchronously to those replicas, and then the router can route traffic across all of these instances seamlessly. So self-healing scenarios, I mentioned this one earlier. Group replication has detection of like a node failing, whether it's the primary or replica. In the case of a primary, a new primary is elected. In the case of a replica, the replica is just sort of disabled from the group. You have network cuts, in which case, like for example, you have a 3-node cluster here, and one of the nodes is like completely cut from the other 2 nodes. In this case, the group will still work because there's 2 nodes here. But you can imagine a cluster, a network cut, where all of the nodes are sort of separated from each other. Or like if you have a 5-node cluster, it's like 2-2-1 split. In which case, MySQL shell, here this is from the documentation, has this utility to force quorum using a partition of. So what happens is, in the case of a 2-2-1 split, one of the nodes will have all the latest data, but it's possible that you reach something called a split brain scenario. Like you can tell the cluster that I want you to use this node here as my primary and use it to seed the other nodes, even though it is a little behind, because that's something that like MySQL shell and the group replication protocol gives the user control over this ability to like do this if needed. This usually happens in a split brain scenario. A split brain scenario is like something like this, like a network partition happens, but then one of the nodes continues getting writes. Or like you tell it that like you're the primary and it gets new writes, and then like there's a split brain because there's conflicts in transactions between the group, and then you can like take one of the nodes and use that as like the seed to your cluster and recover all and synchronize all your nodes with that node. Cluster pause is if you stop all of the nodes at the same time. What should happen is once they restart, when a cluster node is paused or like is killed and then restarts, it comes off as offline. It comes on as offline, sorry. Offline means it still gets all of the replication. It'll get all the data, but it won't like be considered as a primary during election. So like if like all of your nodes are offline, then like that's clear downtime because none of the nodes will be able to accept write traffic. So you can do something called, you can use this utility in MySQL shell called reboot cluster from complete outage. What that does is it will look at all the transactions on all the nodes, figure out which one has the most recent transaction, most recent copy of the data, and then synchronize the cluster such that all the nodes will have all the data from that node, and then it seamlessly will bring up the cluster again. So that was a lot of talk. I will be talking about Juju a little bit, but mostly this will be a demo. So like that's a lot of expertise to build, to be able to run a cluster of MySQL. And the nature of software is like one of the most like powerful things about software is abstraction, is that you should be able to abstract all of this information such that you provide a clean interface to the user that wants a clustering solution, but not have to learn all the details about everything to be able to use it. And so at Canonical, we have this technology called Juju, which is basically an orchestrator. I'll go into demo shortly, but like one thing to note about Juju is that it can work with any environment. So any of those environments, you just provide your credentials, and Juju knows how to interact with that environment. And the idea is that that's kind of powerful, but like that's kind of what Terraform does as well, if you're familiar with Terraform or any other infrastructure as code solutions, but that's not useful in and of itself. The idea behind Juju is that you want to have these things called charms or charmed operators, which are basically units of software that run on Juju. So you can take any software out there. It can be a web framework like Django, Flask. It can be a database, which is what we do at Canonical in the data platform team. We write a charm for MySQL, which will run on Juju. And it sort of helps avoid vendor locking because once deployed with Juju, it's the same software that's running on AWS versus GCP or any Kubernetes cluster. You can automatically, like very easily migrate from one cloud provider to the next without a lot of like issues because the same software is running on them. But the idea is that we want to encapsulate all of this group replication complexity into a simple interface. So here you can bootstrap an environment and then you should be able to, there's a charm store where we register trusted software or charmed operators that we have or the community builds. And Juju will go fetch when I tell Juju to deploy MySQL in 3 nodes, it will go to the charm store fetch the charm, which contains all the business logic around clustering MySQL, and it will run it on each one of those nodes. And then there's an ability to scale up, scale down. Juju provides a clean interface to like sort of use these technologies without knowing what's going on behind the scenes. What do we support so far? So we've been working on the MySQL charm for like about 2 years now. And we so far support scale up, scale down, like through like just simple Juju commands. Like you can scale out your cluster, scale in your cluster. You can take backups or restore your backups. Automatic minor version upgrades, like software, usually there are vulnerabilities and you want to make sure that you're upgrading to new versions when you can. This is for not only security, but also new features that you might want. So like minor versions, you should be able to easily just tell Juju, I want you to take my cluster here and I want you to upgrade it to the next minor version, and it will do it automatically. There's a lot of coordination, a lot of like steps that are abstracted into this like one simple command. There's integration with observability charms. So like you deploy MySQL, you deploy the observability charm, integrate the two, and by default, MySQL will send all its metrics of the node and MySQL to this Grafana nodes, and like you can access the dashboard. So like the idea is you want to make something similar to, we want to make something similar to RDS, but an open source version of it that works across platforms, across all various open source databases. We don't only have it for MySQL. We're working on MySQL, Postgres, MongoDB, Kafka, Spark, OpenSearch, and our goal is to like add more open source databases. Another thing that we handle is secret support. You don't want to be able to store secrets like passwords just anywhere. Like you want to be able to like have proper authorization, which is like username, password, but sorry, that's authentication, but you want authorization. Once you're authenticated into a system, you don't want to be able to do operations that you don't have permissions to. So you want roles for like various classes of like access. We also have TLS support by default. So I'll just quickly demo if people are still interested. I have a shell here on my machine. I have, if you guys are familiar with snaps, snaps are just like containerized applications in Linux or in Ubuntu. So I have a snap installed. I have Juju installed as a snap. I have LXD, which is system, it's called Linux containers, which is like containerization of machines, like it's virtualization, kind of like Docker containers, if you're familiar with Docker containers, except Docker containers have an entry point in one process. With LXD machines, you can have multiple processes and it's like a proper virtual machine. And I have micro-K8s, which is, if you're familiar with Kubernetes, if you're familiar with Minikube, it's kind of similar to that. So if I look at Juju, if I do list clouds, I can see what clouds I have access to on my machine, which is LXD, which I installed, and Kubernetes through micro-K8s. But I can do all clouds, and you can see all the possible clouds you can integrate with. You just provided your credentials for Azure, and Juju will work the same way across LXD, Azure, AWS, so on and so forth. So that's kind of not interesting. I am going to show you how easy it is to bootstrap LXD. So like localhost is LXD, and I'll call it LXD1. That's the name. Oh, that's not good. Wonder what's going on. Okay, well, demo gods are not gracious today. I'll do micro-K8s instead. Why not? Oh, it doesn't like it. Okay. I guess if you guys are really interested in the demo, I can uninstall Juju real quick and Well, I promise it was working a minute ago. Let's hope reinstalling Juju works, because if not, then I'll cry. Oh, I think I know what the issue is. I guess you'll see me debugging what I do for work. Okay, we'll remove it again. And this time I'll install an older version of Juju. What happens at Canonical is we follow waterfall, which is like planning every 6 months. And we're coming up on the 6-month cycle. So what's happening at the company is everyone's pushing new code and things are likely to break. So that's why I'm going to install, hopefully, an older version. And hopefully it will work. Basically, what I wanted to do was I wanted to bootstrap LXD and show you how easy it is to install or like deploy a cluster and actually see it come up without any interactions, and then crash one of the nodes and see it automatically recover. We still have a few minutes, so I can still give this a shot. But if not, you can reach out and like I can show it to you when it works and I figured out what's going on. Any questions? Right, it does. But like if you think about it, it's usually deployed with the application itself. So like usually you use Unix sockets or like you're communicating. If it's on the same machine, then you're using IPC mechanisms, so that it becomes a point of failure. But like usually if something's wrong with the node, you're going to see it. Like what I'm saying is that it's paired with the application. And so like if one of the application instances goes unavailable, the other ones are not. So it's not a single point of failure in that sense. But you can like, in Kubernetes, like obviously you can't pair pods, right? You can. Juju doesn't support affinity rules yet. So like you can, in Kubernetes, you can tell if I have a MySQLRouter pod, I want it to be scheduled on the same node as my application pod. But we don't support that yet. So that MySQLRouter in Kubernetes is like its own application which can scale up and down. So we thought about the point of failure, single point of failure there as well. Let's see if this works now. No, it doesn't.
I guess Wi-Fi is relatively locked down, so
that could be possible. I'm going to use that as my cop-out reason. Any other questions? Yes.
When adding nodes to the cluster, where's the diminishing returns on that, and how do you measure that adding another node might actually impact elections?
Yeah, so there's a lot of things I skipped over when I talked about adding nodes. One of them is like you usually want to add nodes when, for example, there are two reasons I can think of that you might want to add nodes for. One is if in the case of like failure, you want to be able to automatically like fail over, and in that case you're pre-provisioning nodes, and that's for a failure scenario. The more nodes you have, the more expensive it is. With like the less number of nodes, the more susceptible you are to failures. So you strike a balance. Usually we recommend somewhere around 3 nodes, depending on like a 3-node cluster is fairly good. But like with group replication, you can have 1 node in like AZ1 in AWS, AZ2 in AWS, like Lisbon, Rome. They don't need to be in the same data warehouse or data center. So you can distribute it that way as well. The other thing is you might want to like add nodes for like distributing your traffic. And if you're trying to add a node when you're already overloaded, it's going to cause issues, because when you create a new node, what you're basically doing is you're taking all the data from one of the nodes and you're copying it over. That's usually called snapshot state transfer, or SST, and it will put stress on an already stressed cluster. A way to recover, or a way to mitigate against that, is to take backups. So you're restoring from a backup instead, but a backup is not the most up-to-date. It's up-to-date in the past at some point, so that you need to like apply all the patches from the backup till like now, which is called IST, incremental state transfer. You're not doing a snapshot state transfer, it's still there. But like, yeah, exactly. And usually, what was I going to say? I was going to say that like, when you're like adding nodes, you want to make sure that you're adding nodes one at a time, because otherwise, that's something that Charm does, right? Like that we account for, because you could have a cluster of 3 nodes and you just add 3 more nodes, and all 3 nodes are tied up doing SST, and your clients are not going to be able to like access the cluster. There'll be degraded performance. So what you do is like, we actually use MySQL because it's a transactional database. It has implementations of locks pretty well. We acquire a lock, scale up, release the lock. So only one instance can be added to the cluster at a time. Yeah. Sorry.
I'm not familiar with a lot of this stuff. So when you say node, you're talking about database.
Yeah, so a node usually is like, it's usually like if you're talking about AWS, it can be an EC2 node. Like I know RDS has like nodes as well. They have like RDS, like when you provision something with RDS, it takes care of all of this. But when we talk about Juju, we're provisioning EC2 nodes and running software on it.
Okay. I'm also unfamiliar with the concept of the MySQL router. So where would that be in WordPress? If it's
Sorry, where would that be?
in WordPress?
In WordPress.
Yeah, it's in the PHP code, or?
No, so MySQLRouter is written in C. It's a binary. So you can imagine if you have WordPress on like one node or like machine, you have your server, you usually want to keep your databases, it's a rule of thumb that you want to keep them isolated, running only databases, nothing else on there. Like you don't want to run it on your local machine, you want a dedicated server. You don't want to run your WordPress on the same machine as the database, because that can cause degraded performance, like failure scenarios. Right. Your WordPress is running on a different machine. That's where you download the MySQLRouter binary and you run it.
Okay. Thank you.
Yeah. It has the same protocol. So like WordPress, like you can configure it to like access MySQLRouter in the same way you would MySQL server, but it's like it doesn't care. Like it thinks it's talking to MySQL. It's actually talking to MySQLRouter, and MySQLRouter is like proxying traffic.
Thank you.
Yeah.
Okay, any other questions?
Thanks for listening, guys. If you have any
One more
questions,
question.
please feel free to reach out.
So when a node is, let's say you do a planned outage for software updates, and a node goes away, applies its patches, it comes back. In that case, does it automatically rejoin the cluster?
Yes, so there's like a lot more considerations with the upgrades, right? If you have like multiple components like MySQLRouter and MySQL Server, they're like like you can't upgrade router before upgrading the server, because if you have a newer version of router, it may not be compatible with the server. What happens is if you're upgrading the server first, then you upgrade one node, you're basically isolating it from all the traffic, and you're putting it in offline mode so that like it doesn't get elected as primary while it's upgrading, because that's disaster if it gets upgraded and then if it gets elected to primary, it can't replicate all the data to its replicas because it's an older version. So you sort of isolate it, you upgrade it, you have a check that it's okay, you run your checks and like make sure it works correctly, and then you tell the cluster, okay, resume, and then you do one node at a time.
Okay, so there's a
process.
More deliberate process.
Yeah, exactly.
Okay,
But
thanks.
the thing we do is we encapsulate all of this as well. So we provide a way to like tell Juju, okay, I want you to upgrade one node and wait and like let me verify, and then I'll tell you to resume the upgrade. So it's not completely autonomous, it's semi-autonomous, but like it does all of the coordination, all of the steps without you actually having to like interact with MySQL.
One last one. So you talked about like the group replication that only has a single writable node in the cluster.
It is possible, but like I kind of skipped over this as well. Like the one of the advantages of group replication is that you can have multiple primaries. That makes things significantly more complex. But if you think about write quorum, if your write quorum is more than half the nodes, then like it's easy to detect conflicts. So like if two primaries get an update on the same row, they'll make sure that one of the primaries will make sure it can replicate to more than half the nodes, and then there'll be an overlap because your write quorum is more than half the nodes. There'll be a conflict where at least one node will tell the second primary that like, no, there's a conflict, and that will abort, cause an error in the client, and the client will retry. Yeah.
Okay, thank you.
Any other questions? Okay.
Thank you. Thanks.